Okay, so this is the presentation that Seth and I have done regarding chess engines for the AI class. Why can I not move slides? Okay, so the first thing I want to describe is how a chess game can be displayed as a tree, which is why AI algorithms can actually look into it and parse it. So chess is considered a zero-sum game, which means there's going to be one winner, one loser, or a draw. It's a zero expected value game. The reason it can fit into a tree is because there are a finite set of legal moves in any given position. But the reason it's not completely solved is because of the vast amount of possibilities. Even just after 5 moves from each player, there's 7 trillion possibilities. So what the AI algorithms need to do is calculate the best moves, even though there's a huge amount of options. So the first thing that we need to understand is that there aren't actually chess positions in a tree. There are numbers. So we need to understand how the algorithms come up with these numbers. So these numbers are called positional evaluations or just evaluations. And these are what actually gets stored in a tree. So each number would represent the strength of a position. So a strength of 1 would be you already won the game. Strength of -1 would be you lost. Obviously, most positions will be somewhere in between. And this is something that can vary between chess engines. So this is there's 2 main factors with the chess engine. The first is how the evaluations are calculated. The second is what kind of algorithm does it use to parse the tree based on these evaluations. So an evaluation is, as I said, it can vary, but the main factors that are generally used are things like material, which is like how many pieces do you have on the board, how many points are they worth, space, how many squares do your pieces control, king safety, pawn structure, do the pawns defend each other, and yeah. So as I said, the tree parsing algorithms will run on these numbers, not on actual boards. Calculation depth is something I want to bring up with regards to the algorithms themselves. So the depth of a tree would be the amount of moves calculated off of a given node. So let's say we have a starting board. How many moves deep do we want to calculate in order to assign evaluations to? So maybe like a typical human would probably do something like 3 or 4 moves in advance. That's how deep they could calculate. The depth would vary from engine to engine, depending on the power and as well as the efficiency. Computation time increases exponentially with depth. This is quite obvious. I have an example here, like this image up here is showing what I mean by the depth of the tree. So like a depth of 2 would just be, okay, you take a move and then find the next one. Depth of 4 would be you're calculating many, many more moves. And of course, these branches are only branching off into 2 separate nodes, whereas in an actual chess game, it could be branching upwards of 30 or 40. So the high depth in a search is actually the reason that computers are able to beat humans, because they can look much further in the chess tree, the evaluation tree, than humans can. And I want to mention that not all nodes are searched, because there are something called pruning methods, which the algorithms need to use in order to reduce the amount of nodes, because as I said, there are tons of nodes. So we have to get rid of some somehow, and that's done by pruning methods. So there's 3 types of pruning methods that we are going to look at. They are called Shannon type B, alpha beta pruning, and the quiescent search. So what I have here in this little visual is an example of a pruning. So you'll see where there's little red lines. That's saying that, okay, we have determined based on our pruning algorithm or pruning method or whatever we're using, that we don't need to explore this tree. So we can cut that off and make our algorithm more efficient. So the Shannon type B pruning, how does it prune? How does it decide which branches it doesn't need to look down? So what it does is it looks at the evaluation of each immediate node. So it'll take all the possible chess moves from one position, and it'll eliminate the amount of branches, a certain amount of branches, pre-identified or predetermined amount of branches based on their evaluation. So if there's 10 possible moves, let's say they have evaluations of 1 through 10, it'll say, okay, let's take the 3 best, and it will only travel down those nodes. So this was determined not to be an effective pruning method because it was prone to frequent incorrect judgments. So these points here accept high immediate evaluations of poor end results and low immediate evaluations of strong end results. What that means is if a move appeared really strong, let's say you have a move where you can immediately take the opponent's queen, but then you get checkmated the next move, that would be considered by this pruning method because it would only look at the evaluation of the next move. I took his queen, strong evaluation, even if it immediately leads to the downfall. And then same with the contrary. If a move looked bad, like, oh, maybe you're sacrificing a piece, but it could lead to checkmate, it wouldn't see that. It would say, you're sacrificing a piece, low valuation, we don't need to search that tree. So alpha beta pruning is an upgrade to this. It kind of changed the way algorithms are searched through. Or sorry, trees are like parsed in which branches get cut off. So it replaced Shannon type B and is actually used by what we have researched to be the strongest chess engine in the world. So what happens in an alpha beta pruning is that basically when it starts looking through each branch, it will kind of like assign a highest value and a lowest value for each node. So I'm actually just going to use this example here as a visual. So let's say we're searching down from A to B, and then we get to D. So we want the minimum value of this next layer. So you see where it says terminal node, and it says on D we have 2 and 3. So it would look at it and say, is the highest value of D lower, or is the highest value of this lower than the lowest value of E? And if it is, we don't need to look at E because we know that all the values of D beat out E. So we can just cut off E and we wouldn't have to search through that. So that's basically what the alpha beta pruning method does, and it's an upgrade on the Shannon type B because it actually takes into account the deeper evaluations rather than just what the position appears to be based on a single evaluation.
All right, this is the quiescent search, and it seeks to limit the horizon problem that AI can deal with. And this issue is when you're expanding to the very edge limit of your tree search. So for example, in the min-max, there's a certain depth that you're going to go to no matter what, regardless of all the pruning that's gone on before. And one branch could look really promising. So as an example, let's say your queen gets to take the bishop, and that's the final move in the search tree. So that would be evaluated very strong. It looks like a good move. You get to claim their bishop with your queen. But what you don't know is the very next move beyond the limit of your search reach, aka the horizon, the opposing player gets to take your queen, which is very bad. It's significantly worse probably than taking the bishop. So what this quiescent search seeks to do is behave similar to how a human would work in a chess game and reject a move that's bad, and ones that are promising or are critical or have some kind of significance to us, like a capture move. It actually explores further and extends beyond the frontier and explores the search possibilities on that specific path further to try to mitigate these kind of risks. So in this case, it would explore further past the capture move, but another more benign move, like say, a pawn to just some random corner that isn't really going to be challenged or die, it's not going to explore further. And the reason for this is it saves us adding more just general depths to our tree, right? That would be an exponential increase in problem space if we just said, oh, we're just going to scan more. You're always going to have a frontier somewhere. If you scan to 10, you scan to 20, whereas this lets us selectively scan further to solve this problem. Okay, and then apart from that, there's also different search algorithms that kind of approach this problem space of searching this tree differently, and they have different results, different strengths, different speeds of running. So another option we have is the Monte Carlo search algorithm, and this one in some ways is seen as an improvement, although you'll see as we discuss further that there's pros and cons to both, but this has some potential benefits in terms of the amount of evaluation time and how many nodes are going to be evaluated as it operates. So it has a different method, and it works by, instead of scanning through everything at every layer, it tries to determine promising moves and explore them further forward and expand them with random sampling rather than going through each layer by layer. So it's kind of like the quiescent search in some ways. It's a little more focused, and it travels through 4 distinct phases, which we'll delve into more detail going further, and that is selection phase, expansion phase, a simulation phase, and then a back propagation phase where it saves the results of what happened and uses that to inform the next decision going forward. All right, so the selection phase of the Monte Carlo actually has two kind of negative and positive, kind of a pro-balance thing going on to make its decisions. So the first thing it does is it has an exploitation kind of balance to it and an exploration side to it, and it kind of balances between these to try to make a best decision. And first of all, I just want to point out, actually, in terms of expanding on the most promising route, it uses heuristics to determine what route to first choose that could be the best one. And then from that route that it expanded on, it now wants to go through a bunch of nodes and decide which one to kind of has this highest upper confidence bound. And it does that with this algorithm here. And there's two parts of it that have the exploration and the exploitation. So the exploitation side tries to pick a safe mode that is going to be that leads to like the best results in general, and that's done with the QTA side of the formula. And that's basically saying like, okay, the A node has had significant success in the past. It has a highest success in the past out of all the other nodes. And then the other side of that, the NTA part of the formula, is our exploration. And that means that the node hasn't been tried very often. So it's kind of like a promising node that hasn't been tried a lot. So maybe there could be some unexpected result by trying that. So rather than just going all of the safe, bread and butter white options all the time that are known to be good, we're also going to dash in a little bit of exploration and try a move that's unknown, maybe a little more risky, but could lead to great results. All right, the expansion phase. We then, at a given node, at the end of our leaf of the whole tree, we want to expand some positions on that node as like new territory or frontier that's been discovered. And so the basic idea is, like, your simplest version is you could just add a node every time you run a simulated game down through a given path. And this node would be the first node that you've encountered that hasn't been stored before. There also are more kind of advanced versions where you would add more or have some kind of heuristic to determine which node should be added. But either way, the idea is just to open up your problem space a little bit further. And then the simulation round. Once you've reached the end of a node, the algorithm actually plays a full game to fruition, and it either results in a win, a loss, or a tie, again, because of the zero-sum nature of chess. The simplest kind of version you can have with this is that you just make random moves till you reach an end of a game, whatever it is, and then you just take that result. However, that's kind of like basic and doesn't really to the strongest results overall. And an improved version of this is to apply some kind of strategy. We're going to add in some heuristics, maybe derived from like experts or pros at playing chess. And we can also throw in like patterns that are common or like some capture plus minus considerations, or even like analyze the proximities close to your piece. Are you under attack, or other kind of plus minuses that can be made against it. And then employing that strategy, you can play it a full game using these strategies, and then again allocate either a win, a loss, or a tie, which is going to match to a win being a +1, a loss being a -1, or a tie just being a 0. And then this leads us to the final stage, which is our back propagation. We're going to take the results of that simulated game at a leaf node, and we're going to back propagate it up through the network or the path that was followed from root to leaf of the entire graph. And we're then going to take our either +1, -1, or 0 and have some kind of strategy that's going to save this data all the way back through the path. So a super common, and it's found to be really strong, propagation strategy is to average at each node the value of each simulated game that passed through that node. So if you had one game that came through a particular node, and it was a win at the end, you would have a 1 there. And then if it was a loss, it'd be a -1. And so then you kind of start to get an accumulated knowledge of how well this node fares later down the road in the future. So it can improve the overall decision making collectively, kind of a collective memory at each stage.
Okay, for our code implementation, what we did is, we didn't write the code ourselves. We found some code online that ran some algorithms in a tic-tac-toe game. So chess is obviously very complex, and we wanted to just kind of develop like a proof of concept. And so tic-tac-toe shares these same values that chess does, in that it's a zero-sum game. You have a certain set of legal moves, and you can represent every single game by a tree. So we did reduce our complexity here by going with tic-tac-toe, but it has all the same concepts as a chess game would. So what we did is, within the script that we had online, we tweaked it a little bit in order to actually run the algorithms that we wanted to do. So what we did is we ran So we made a bunch of matchups. So here it says 1,000 sample games for each matchup. So an example of a matchup would be a Minimax algorithm playing against the Monte Carlo algorithm. That's an example of a matchup. I think we had 6 total. And yeah, so we ran all these matches, 1,000 games for each, and we will take a look at the results. Okay, so this is, as you can see, playing random versus random. X wins 55% of the time. Interesting, because I thought it would be a little bit more even, but 13% draw. So this is literally just random moves. This is playing a Minimax algorithm against itself. We have 0% wins on either side and 100% draws. And the Minimax, when played against random moves, was able to win 80% of the time and draw 19% of the time, and zero losses by the Minimax algorithm against random moves. This is the implementation for the Monte Carlo. So similarly, we played it against random moves, in which case it was able to win 60% of the games and not lose a single one. We played the Monte Carlo algorithm against the Minimax algorithm, where we observed 100% draw rate. And finally, we played Monte Carlo against itself, where again 100% draw rate. Okay, so after running these algorithms, here are some of the findings we had. So the algorithm was played with a 100% precision rate. In a tic-tac-toe game, if both sides play perfectly, the game will always result in a draw. And that is what we observed from both the Minimax algorithm and the Monte Carlo algorithm. So they both drew 100% of the time when played against themselves or each other. They never ever lost to random moves. Monte Carlo won 60% of the games against random moves, and Minimax was able to win 80%. Probably just like they play the same way, so I'd imagine that's just like an outlier. Occasionally drew against random moves, yeah. Sometimes the random moves just happen to be the optimal set. And yeah, Monte Carlo drew more than the Minimax did.
All right. So then, in conclusion, from our test findings, because we could parse, or because the algorithms could search all the way to the end of the game, that's why we noticed these 100% success rates, or occasional draws, but they always know all the way to the end. So then the difference is, when applied to a chess game, our search space is exponentially huge. In fact, I think I saw somewhere they stated that the maximum states that could be possible in chess game is equivalent to the number of atoms in the world. It's absolutely huge. We cannot compute this. This is where we start to see the differences then between the search engines. They can't know the end, and so some of these trade-offs are going to come into play in terms of their success, or they can actually lose to each other more often. What we found then is, out of our research about these top chess engines, is that in 2020, the Stockfish engine was considered the top engine. It uses a Minimax to search over its search tree of data, and then it also uses a database of pro moves to kind of embed the strategy in there, right, when it's selecting nodes as its heuristics.
I just want to jump in here and say Stockfish also use the alpha beta pruning method that we talked about earlier.
True say. Certainly need to reduce the search space of that. And then the second strongest in 2020, the Leela Chess Zero, uses the Monte Carlo search. So it's using the more promising search technique and not expanding on every single branch available, which is interesting. So both very strong engines, and you can see that they can use both search to great success. And there's also a lot of other factors we want to point out in this. So just looking at the search tree algorithm itself isn't enough to conclusively really point one way or the other. And then recently, Google's AlphaZero is actually able to beat Stockfish, and they went with the Monte Carlo algorithm, which is interesting. But in post using a database of pro moves, they used a neural network to produce some of the heuristics in the decision-making process. So that could have made their advantage potentially over top of Stockfish's previous kind of design. And so for us, in conclusion, it's hard to choose a conclusive, Monte Carlo's better or the min-max algorithm is better. It's definitely more than just the raw search algorithm that comes into kind of the conclusive implementation. The Minimax does seem more powerful overall in kind of a raw sense, we noticed. Certainly in the tic-tac-toe game, it seemed to win a little bit more. And also from these chess engine research, just in a straightforward implementation, it seems that the min-max also wins a little more frequently. And I would suggest that that's probably because it actually searches through all the options at a given level. So if your depth is deep enough, you're probably going to get better results. And the Monte Carlo can definitely save you time in evaluation when the branches and the state space is absolutely enormous. It's going to really help you hone down on just promising options.
So another reason that it's basically impossible for us to select a clear winner just based on the chess engine is like before we even get to use the tree parsing algorithm, first step is evaluating positions based on their strength. And both of these engines are using specific heuristics, like variety of heuristics specific to them. For example, maybe one algorithm values king safety very strongly and the other algorithm doesn't. And then it produces the evaluation the same way. So like they're going to have significantly different values in the trees before they even get to the point where the algorithm needs to parse it. So there's just too much for us in a chess engine for us to actually identify, okay, this algorithm is better because the chess engine's better. There's too many factors for us to make that conclusive decision. I guess that's it.